Today, we're going to focus on two additional theorems that can be applied to differentiation, and that is the mean value theorem and Rolle's theorem. So we've talked a lot about derivatives, and we've talked about that the most common definition of a derivative is the slope of a tangent line at a specific point. And in Algebra 1, Geometry, Algebra 2, we've talked about the fact that slope can be termed as the rate of change. All right, slope can be termed as the rate of change. And in calculus, we can actually talk about two different rates of change. The two different rates of change is the average rate of change and the instantaneous rate of change. So let's talk about what the difference is. All right, the first thing is that the average rate of change will always be along an interval, where the instantaneous rate of change will always be at a point. Okay, so let's think about that in respect to the graph that we see above. Okay, this is the graph that's generated from the data table listed. All right, now if we're looking over an interval, and let's talk about, let's say between the interval of 4 and 8. If we're looking over the interval of 4 and 8, and actually let's do 4 and 10 to make this clearer. If we're looking for the average rate of change within that interval, we would draw a line like this to recognize the average rate of change. Now, that average rate of change is the result of a secant line, okay, because it crosses through 2 points of our graph. And so when you hear the term average rate of change, you are thinking about the slope of a secant line. Okay, it is the slope of a secant line. So what's important about this is on an interval of AB, the average rate of change is equal to f of b minus f of a all over b minus a. And this should be reminding you of how we've been able to identify the derivative at a certain point from data tables. We've been finding the average rate of change. All right, and often it is abbreviated as AROC. So if you hear someone talk about AROC, you're talking about the average rate of change, which you're using the slope formula. Now, if we're looking at the instantaneous rate of change at a point, so let's say we're looking at the point 14.5. The instantaneous rate of change would occur based off of this line. And here we should be recognizing that this is the slope of the tangent line. This is the slope of the tangent line. All right, which means that the instantaneous rate of change is always going to be equal to finding the first derivative at that a value. All right, and this is known as IROC, instantaneous rate of change. So depending on what the question asks you determines how you find it. All right, so for example, here it says find the average rate of change of f of x on the interval 2, 12. All right, well, the average rate of change is going to follow the formula of f of 12 minus f of 2 all over 12 minus 2. If we looked at the table, f of 12 is 8, f of 2 is 5, and so we are going to get the average rate of change to be 3/10. Okay? Now, when we're talking about the instantaneous rate of change, you could be asked a question like this. is the instantaneous rate of change at x equals 4 greater than the rate of change at x equals 6? All right, well, let's look. Instantaneous rate of change at 4, so we could draw a line right here. Is that greater than the instantaneous rate of change at 6? Well, we can say yes, because the tangent line drawn at 4 is steeper than the tangent line drawn at 6. All right, so now that we can find the average rate of change and the instantaneous rate of change, all right, we need to talk about the two theorems that are associated with this. And the first one is known as Rolle's theorem. And what Rolle's theorem states is if f of x is continuous on the interval AB and it's differentiable on the interval AB, okay, and the value of f of A equals the value of f of B, then there is, hold on, something, then there is guaranteed to exist a value of C on the interval AB in which the first derivative equals 0. Now, this means that there must be a relative max or a relative min on the original function within the interval AB. And that makes sense because if f of A equals f of B, we're returning back. So let's think about the previous function, okay? Does Rolle's theorem apply on the following intervals? Why or why not? So when we look at our previous function, we know that our graph is continuous and differentiable, all right, from 0 to 16, okay? So we've already met the first two conditions. Now, we have to determine, does it apply in the third condition? Does f of 2 equal f of 14? Okay, does f of 2 equal f of 14? That's the first question. So when we look at f of 2 equals 5, f of 14 equals 5, and so the answer to that is yes. So how would you answer this? Well, you would answer by saying Rolle's theorem is applicable for f on the interval 2, 14 because f of x is continuous on the interval 2, 14, differentiable on the interval 2, 14, and f of 2 equals f of 14, which equals 5. All right, so then the question is there a value of C in which the first derivative will be 0? So because we're saying Rolle's theorem is applicable, that means that there is a guaranteed C value in which the first derivative will be 0, which means that we'll have a relative max or min in our original function. Well, if we look at our graph, if we look at our graph, we absolutely do have a C value in which we will have a first derivative equals 0. And that C value is 8. All right, so we could say the guaranteed value of C is 8. Now, if we looked at the interval between 2 and 8, we already proved it's continuous. We already know it's differentiable. So we have to prove, does f of 2 equal f of 8? And the answer here, well, f of 2 is 5. What does f of 8 equal? Well, according to our table, f of 8 equals 11. So this case, we can say no, Rolle's is not applicable because f of 2 does not equal f of 8. And the key thing to this is we are then proving that there's no relative max or relative min within that interval. And our graph supports that. If we look between 2 and 8, there's no relative max or min in this interval at all. So Rolle's theorem supports what we've been doing with the first derivative test. All right, so let's look at number 1. Let's determine whether Rolle's theorem is applicable or not, and if it is applicable, apply the theorem to find the values of C guaranteed to exist. So, first things first, okay, is this function continuous? Well, it's a polynomial, so we know it's continuous. So we can say it is continuous from -3 to 0 because it's a polynomial. And we know it's going to be differentiable in this interval because there's no cusp located. So we can absolutely find that. So the first two conditions are met. We need to find the third condition. And the third condition is, does g of -3 equal g of 0? So we're going to work that out. G of -3 equals 9 times -3 squared minus -3 to the 4th. So we're going to get 81 minus 81, so that equals 0. G of 0 is 9 times 0 squared minus 0 squared. Oh, that equals 0 as well. So G of -3 equals G of 0. It all equals 0. Therefore, Rolle's is applicable. So now we have to find the C value in which this theorem is applicable. So to find the C value, okay, we know that the first derivative of C equals 0. So let's find the first derivative. The first derivative of g of x is 18x minus 4x to the 3rd. All right, and then we're going to set that equal to 0. We're going to factor out all right, and I get x equals 0, and I get x equals plus or minus 3 over the square root of 2. So that's 3 different possibilities as an answer. So how do I know which one is the right C value? Well, the first thing we can cancel out is the positive 3 over square root 2 because that's outside of our interval from -3 to 0. We can also cancel out x equals 0 because that's one of our endpoints. And your C value can't be an endpoint of your interval. So our final answer here is -3 over the square root of 2. All right, go ahead and try this next one on your own. Determine whether Rolle's theorem is applicable, and if it is, find the value of C. Now, based off of these problems that we've been doing, we should recognize that Rolle's theorem is determining an instantaneous rate of change being equal to 0 because we're looking at the idea that it's at exactly this point that the first derivative is equal to 0. The next theorem we're going to look at is the mean value theorem. And the mean value theorem is very similar. In fact, Rolle's theorem is a specific case of the mean value theorem. So what does the mean value theorem state? Well, the mean value theorem states that if f of x is continuous on the interval AB and differentiable on the interval AB, then there is a guaranteed C value to exist on the interval AB such that the instantaneous rate of change is equal to the average rate of change. So it's not that the instantaneous rate of change at C is equal to 0, it's that the instantaneous rate of change is equal to the average rate of change. So let's look at this example. Consider the function h of x is equal to 3 minus 5 over x. The graph of h of x is pictured below. Does the mean value theorem apply on the interval -1 to 5? Explain why or why not. All right. So in this case, from the interval of 1 to 5, all right, we have to make sure that it is differentiable and continuous. All right. So from 1 to 5, it is definitely continuous and it is differentiable. There's no cusp there. Okay. So the first two conditions are met. Okay, first two conditions are met. So what's important about this is h of x is not continuous at x equals 0. That's the only value that it's not continuous. All right, so we know that we've met the continuous and differentiable factors. So now we have to figure out, does the first derivative equal the average rate of change? All right, does the first derivative equal the average rate of change? Okay, so we can say yes right now here for this question because it is continuous and differentiable at the interval 1 through 5. So what does that guarantee graphically, okay, for the function? Well, what that graphically means is that the average rate of change equals the instantaneous rate of change at some point. So we could draw this tangent line, and that could be the same as this tangent line. They're parallel. Okay? So that means a value x equals c where the tangent line is drawn to h of x is parallel to the secant line passing through our interval values of 1, -2 and 5, 2. Okay? So let's do that with an algebraic problem and not a graph. Apply the MVT to find the values of C guaranteed for h of x on the interval 1 to 5. All right, well, we can find the average rate of change by doing our slope. All right, 2 minus -2 all over 5 minus 1. So we get 4 over 4, okay? So we get 1. So we know, all right, that the derivative of h of x equals 1. So let's find the derivative here. All right, so we know h of x is equal to 3 minus 5x to the negative 1. So let's find the derivative. All right, the derivative is going to be 0 plus 5x to the negative 2, and that's going to equal 1. So 5 over x squared equals 1. All right, so we get 5 equals x squared. So x is going to equal plus or minus the square root of 5. Okay, we know it's not going to be the negative 1 because that doesn't fall into our interval. So our C value, okay, in which the mean value theorem applies, is the square root of 5. Okay, I would like you now that we've used the mean value theorem to do the next one on your own. Explain why you cannot use the mean value theorem for the function f of x is equal to x to the 2/3 minus 2. Okay, so let's do one more problem together. Find the equation of the tangent line to the graph f of x is equal to 2x plus sine x plus 1 on the interval 0 to pi at the point which is guaranteed by the mean value theorem. So essentially, we have to do it. We need to find this C value. That's what we need to know. So we know with the mean value theorem, the first derivative at some C value is going to equal the average rate of change. So f of pi minus f of 0 all over pi minus 0. All right, so if we found the first derivative of f, it would be 2 plus cosine x is equal to, well, f of pi is going to be 2 pi plus 1. F of 0 is going to be 1. And it's going to be over pi. Okay? So we end up getting 2 plus cosine x is equal to 2. So cosine x is going to equal 0. And we know cosine x is equal to 0 at pi over 2 and 3 pi over 2. But 3 pi over 2 falls out of our interval, so we know our C value is pi over 2. Okay? Our C value is pi over 2. All right? So we need to find the y value of our point of tangency. So it's going to be pi plus 1 plus 1. So it's going to be pi plus 2. All right. We also need to find our slope of our tangent line. All right. So we're going to use our first derivative, 2 plus cosine x, but our x value is pi over 2. So we're going to get 2. And so our equation will be y minus pi plus 2 is equal to 2 times x minus pi over 2. And that would be your answer. Now the key thing with the mean value theorem, and I've said this multiple times, for the mean value theorem to be applicable, the instantaneous rate of change is equal to the average rate of change, okay, at that C value over the interval. That's it for today. Good luck on the worksheet. Have a great day.